Okay, so this is what we were talking about last time. This result is going to be important where I want to go today. So you have integral domains R inside T, U is some unit in T, but I and R be a proper ideal, then this ideal survives, which means it doesn't blow up. It's still a proper ideal, either here or here, or maybe both. So if not, so we started the proof, and I'll go through what we went through. If not, there exists AI and I, well, let's see, AI, BJ, and I, such that, so if this ideal I blows up in both of these rings, then A0 plus A1U plus A2U squared all the way up to ANUN is equal to 1. So there has to be a 1 in the ideal I lifted up here. And B0 plus B1 U minus 1 plus B2 U minus 2 plus BM U minus M is equal to 1 as well. So it blows up in both of these. Here we will assume that N is greater than or equal to M and is minimal. So this is minimal in that sense. And of course, this is symmetric because if M is bigger than N, then I can just reverse the roles, U and U inverse. Right. Okay. So this is, I always have to look down to make sure that I'm multiplying by the right thing. But what I'm going to do is I want to multiply the second equation. I think by U to the N is, I'll multiply that by U to the N and rearrange a bit to obtain, so I'm going to write down what I got and we'll talk through it. I get 1 minus B0 U to the N is equal to B1 U to the N minus 1, B2 U to the N minus 2, all the way down to BM U to the N minus M. Okay, so let me see if I can kind of pull apart what we did here. So I'll multiply this sucker by U to the N. So I'm going to have a U to the N here and a B0 U to the N here, which explains this term, because I sucked up B0 U to the N over the other side. And everything else is just kicking this up by U to the N. Everybody okay with that? So that's just a little bit of a rearrangement there. And now multiply the first equation by 1 minus B0. Yes. To get, well, I'll make this easier. 1 minus B0 times A0 plus A1U plus ANUN with 1 minus B0. And what I want to do now is substitute for 1 minus B0. I'm going to make sure this is what I'm going to do here. Right, to get this. U. Plus all the way up to AN miss here. One. Right. Right. So what did I do here? Actually, it might behoove me to put in another term here. So what did I do here? Let's take this apart. I multiply this 1 minus B0 out, getting me all the way up to here, right? And then I have a 1 minus B0 AN. So there's the AN part of it. And the 1 minus B0 part is, well, 1 minus B0 UN is this part right here, which is where this comes from. Because remember, this term here, right here, is going to, this last term is 1 minus B0 AN UN. And so using this right here, this is just AN times this mess here. Everybody okay with that? Is equal to 1 minus. Anybody see what a mess. Anybody see what we've accomplished here? Now take B0 over the other side. Plus 1 minus B0 AN minus 1 plus AN B1 UN minus 1 plus BM U to the N minus M is equal to 1. Right, agree? Notice that highest appearing power of U is N minus 1. Everybody agree with that? Because here the powers of U go up to N minus 1, and here they peak at N minus 1, right? And this contradicts minimality of N. Because now, after massaging this equation, I have a small one. So it's an inductive argument. Everybody okay with that? Hence, that proves the theorem that, so if you have an ideal in R, that it survives neither RU, proper ideal, that it survives neither RU or U inverse. Okay. Any questions on that? Okay, so we're building to something here. This just gets better and better. So here is a big piece to a beautiful theorem that I am going to reveal in a moment. Theorem 15.2.8. Let R be a domain with quotient field K. if I is a proper ideal, there exists a valuation overring of R where I survives. There exists a valuation overring. The of R, in which so in other words, if I've got some proper ideal of any integral domain, then it's guaranteed to stay a proper ideal in at least one valuation overring, right? This is not an obvious theorem. And in fact, it's going to require our old buddy Zomer.
What is the valuation over?
It's you know, is it the word overing you convert?
Yes.
Okay, I'm sorry about that. So definition. What are the a domain with quotient field K? An overing bar is a ring, well, it's a domain T such that so it's just something between it's a domain between R itself and its quotient field.
So R is its own overing as well?
R is an overring of itself, right? The only overring of a field is the field itself, right? So notice that take care here because T consists of fractions, right, by definition. But that doesn't mean that T is a localization. In fact, for the ring on the street, an arbitrary overring does not have to be a localization. It consists of fractions, but it's not localization, it's a set. In fact, there's a type of integral domain called a QR domain in which every overring is a localization, and these domains are very rare. Okay, so looking at the theorem in this light, there is a ring, there's a valuation ring between R and its quotient field such that I survives there. So let's prove this. Now, what we're going to do here is I am going to show that there is a maximal overring of R in which I survives. And guess what it's going to be? It's going to be a valuation domain, right? So first, so strategy step one, we show there exists an overring of R maximal with respect to the property. That I survives. So what that'll mean is there's this big ring in which I is still a proper ideal. In any ring that contains that, I blows up. Okay, so this sounds like a job for Zorn, and it is. So I'm gonna consider all pairs. So I'm going to call it R sub J, I sub J. where,
Plus,
uh,
plus,
RJ is an overring. IJ and RJ is a proper ideal. And I is contained in IJ. So this is sort of like, and this is going to be actually a huge set because, for example, if I survives up here, then one of the IJs can be I times RJ, but there might be bigger ideals. So the pairs aren't necessarily unique to the index. So there might be a whole bunch of pairs with RJ, right? And there might be a whole string of ideals that I can fit in here, right? So it's all these possible pairs of overrings that have a proper ideal that contains I as a set, right? I am going to put a partial ordering on this. This set gamma, I'm going to call it set gamma, via any ideas on how I want to do this partial ordering?
yeah. Contain,
Which contain
plus containing that data.
we need more. How about both? So I partially ordered this. This is sometimes called the product ordering. Right. So the way we compare these is we're going to say this one's smaller than this, if and only if this ring is contained in this one, and this ideal is a set is contained in this one. And remember, they both have to be proper ideals. Okay, I want to apply Zorn. So let's go through and actually show that you have every chain has an upper bound, at least briefly. Let be a chain and so I'm gonna, let's see, I need a creative index set here. R alpha, alpha in some huge index set. Gamma. Now, since this is a chain, R alpha, I alpha is less than or equal to R beta, I beta. Or the opposite, R beta R alpha. Everybody okay with that? That's what it means to be a chain. It means that these aren't just apples and oranges, they're all apples. If I pick them up a chain, so any ordered pair, R alpha, I alpha, and R beta, I beta can be compared. One of those two things must happen. Let's let U I hat equal well, Let's do it this way. I'm gonna take the sucker right here. And I claim that this is the maximal element of the chain, or this is, I'm sorry, not the maximal element, this is the upper bound of the chain that we seek. Notice that for all alpha and gamma, R alpha is contained in U, and I alpha is contained in I hat. Right? So R alpha, I alpha is less than or equal to U I hat for all alpha in the index set. So in other words, this thing is definitely going to be an upper bound if we can prove that it's still an element set, right? It's still got to be in gamma. So why is it in the set? Well, let's see, what do we got? What does it mean to live in this set? What does it take for membership? Well, let's see. We need R to be a ring, an overring. Notice that. And of course, because every one of these R alphas is in K, so their union is in K, and every one of these R alphas contains R. So it's where you want to be. Maybe the puzzling thing is, why is it a ring? Can somebody explain that to me? Why is this union a ring? I don't generally expect unions of rings to be rings. But here, there's something special going on. That's right, it's a chain, right? And so if I have two elements in U, one of them's in R alpha and R beta. So if R beta is the biggest one, they're both in R beta, so there's sums in there, and that's essentially solves your problem. Yes.
Is it also because all of these are subsets of K, and so you'll at least have this as a subset of K?
Well, that's exactly right. Each R alpha is an overring, so it's all a subset. Okay. So I've got that U is a ring. I've got that it's an overring, right? It's between R and K. I need I hat to be a proper ideal. So similarly, I hat in U is an ideal. For the same argument that we gave before, it's a subgroup. And why does it suck? Why is it a vacuum cleaner? Well, if you multiply something in U times something in I hat, that element U came out of some, right. The element from U actually came out of some R alpha, and the element of I hat came out of some R beta. If R beta is the bigger one, that means that both R and the element from I hat are in that R beta, so it's sucked into the I business, whatever I beta, and so it's in U, right? Everybody okay with that? And is proper as one is not in R alpha, all alpha. So one's in none of these, so it can't be in the union. Whoops. That was a very nice look, Sophia. That's all you had to do. Yes, one is not in any of these ideals, right? So do I have it licked? It's proper ideal, things, blah, 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 blah. Okay, good. So this pair is actually an upper bound that's in the set. So by Zorn, there exists a maximal element. So I'm just going to define this maximal element. I'm going to call it VJ, that pair. Let VJ be such a maximal element. So V is maximal such that I survives. In V, and I is in J, which is a proper ideal of V. Okay. So I've got this taken care of, except I really need to show that V is valuation domain. So I'm gonna do this as follows. Suppose V is not a valuation domain. Then there exists alpha in the quotient field such that neither alpha nor alpha inverse is in the. So that's one of our equivalent characterizations of valuation domains. If you have a non-zero element of the quotient field, either it or its inverse has to be in the valuation domain. So if V is not a valuation domain, I should be able to find some alpha in the quotient field such that neither alpha nor its reciprocal are in V. But notice, since J in V is proper, J survives in the alpha or the alpha inverse. And there's that theorem, right? Am I okay with that? So, since I is contained in J, then I survives in the alpha or the alpha inverse. This is a contradiction because V was maximal with respect to the property that I survives. Hence, V is a valuation. So this gives us the theorem that we want. There's a valuation overring for which there's a valuation overring in which a given proper ideal survives. So here is this is one of my favorite all-time theorems. I should throw a date on this thing. Theorem 1529. What are the domain with quotient field K? Remember, the integral closure is just the set of everything in the quotient field that happens to be integral over R. The integral closure is the intersection of all valuation over rings bar. The integral closure of any domain is the intersection of all valuation over rings bar. What the heck does that have, right? I mean, the integral closure is just a collection of all these things that are root of some monic polynomial somewhere. This actually is exactly the intersection of valuation over rings. This is an amazing and useful theorem. So let's see why this is true. One of the containments, as you might expect, one of the containments is decidedly easier than the others. Let's let omega in K be integral over R. And let V be any valuation over it, right? So if it's integral over R and V is a valuation overing of it, it's integral over V because R is contained in V. I only need coefficients from R to make it integral. I've got more choices for coefficients here, right? Everybody okay with that? But V is integrally closed. We proved that last time, I believe. So omega is in V. Therefore, omega is in the intersection of all valuation of those. That wasn't too bad. Just hinged on the fact that V happens to be integrally closed. By the way, this is much harder, and in fact, not true. But understanding it for complete integral closure, it's much more a complicated mess. Here's the interesting direction. Why is it the case that if you have something, so if you have something that lives in every valuation overring, why does it have to be integral? Well, to this end, let's suppose that omega lives in the intersection of all valuation overrings of R. I want to show somehow that it's integral, and I'm going to use one of my characterizations. We will show omega is in R, omega inverse. And okay, let's assume this is not zero, right? Because obviously zero is going to be in any ring, so there's nothing to prove there. Remember, this is one of our characterizations of being integral. If omega is in R adjoint with omega inverse, that means that it's an integral element. So how are we going to show that? Well, if not, then Right, okay with that? So certainly omega inverse is in R adjoint with omega inverse. And if omega is not there, that means that omega inverse is in fact a non-unit, which means that that ideal is proper. Right? So omega inverse survives in some valuation overing. V containing R. Well, let me be more explicit. V containing R omega inverse, which contains R. Are you okay with that? Yes.
If omega was the identity, like if it was one, like isn't that also? Or like what would happen if omega was? Oh, then it's a proper ideal.
Correct. You answered that before I could even read it. Okay, other questions? So right? And this implies that omega is not in V. So there exists V, evaluation over a bar. Such that omega is not in V, and this is a contradiction. Because omega had to live in every valuation over of R. Therefore, the integral closure is equal, in fact, equal to the intersection of valuation of R's. That is a stupefying theorem. Okay, any questions?
Dr. Kalina?
Hmm?
So we were using the ultimate characterization of integral closure essentially, where
Yes.
Okay.
Or alternate characterization of what it means for an element to be integral. Okay, this makes life sometimes easier. Here's one application. I'm not, it's too carefully, but I'll show you. Nice application. Theorem, I think this is earlier in your notes. I told you this, but I won't repeat it. If R is integrally closed, so is Rx. So the property of being integrally closed is preserved when you go to polynomial extensions. So why is this the case? Well, the first thing that I would like to notice is this. And of course, implicitly here, I'm talking about domains. If K is the quotient field of R, then Kx is a Can anybody fill in the blanks for me there? Why is Kx integrally closed? Don't look for anything too fancy. What kind of if K is a field, what kind of ring structure does Kx have? PID. What do you know about PID? We'll take it down a notch.
Well,
PID is the
valuation.
UFD. What's that?
The PIDs are valuation limits.
No, that usually not. A PID is a valuation domain if and only if it's local. You only have one non-zero. But a PID is a UFD, right? What do you know about UFDs? They're always integrally closed. In fact, they're even completely integrally closed. But here's the point. So the integral closure of Rx must be contained in Kx. Because anything that's in the quotient field of Rx is also in the quotient field of Kx, but this is already integrally closed. So anything that's integral over Rx is integral over Kx, and so already almost must be. So the upshot is when you're looking for the integral closure of Rx, what you have to worry about is really the quotient field of this is K round brackets X. It's rational functions. But the observation that this is integrally closed means, hey, I don't have to worry about anything except polynomials. No rational functions allowed, so to speak. And I'm going to make another observation, and that is I'm going to now make this claim. Since R is integrally closed, R is the intersection of all the valuation overrings of R. All right. So I claim Rx is the intersection of Ax. So I'm just going to take this up a notch here. R is the intersection of all these. Basically what I'm saying is I can adjoin a polynomial variable to this identity. Check this. It's actually fairly easy to show both containments. Right? So to show this, we also know that any intersection of integrally closed domains are integrally closed. So if we can show each Vx is integrally closed, then we have Rx is integrally closed. And this is because we have the theorem that says if you intersect any family of integrally closed domains, you get an integrally closed domain. So if it's true that each of these is integrally closed, then the intersection has to be integrally, right? So the last step is Y is Vx integral closed. Well, let's take an element. Not necessarily V integral. suppose that I have something here, that's integral of Vx. Now, again, this has to be in the quotient field in general, but we just made the observation that anything that's integral has to already be in Kx. So that's made our lives a little bit easier, right? Notice each Ki in is in V, right? Right? If all the Ki's are in V, we're done. If not, subtract off all Ki, Xi, and V. Why can we do that? Because sums of integral elements are integral, right? So if some of these coefficients are in V, maybe some of them are not. I'm going to pull off the ones that are in V, leaving me only ones that are not, right? And I can do that because we're assuming that this is integral. And so when I add all the stuff in V, that's integral. So I can basically reduce this down to where none of them are. So now we have Kix I1 Xi1 plus Kim Xim I1 less than I2, and each Kim is not a V, right? Now, look at the values of this. And find the smallest. And pull that out. So what you're doing is you're finding these values. These are all negative values because they're not in V. So you pull out the largest negative one. Let's say Kij times, I'm going to re-index this, V1, let's say VL1 X L1, well, I guess the powers will be the same, plus V LM XI. So if I pull out the largest negative, these are all, this is in Vx, but it has a negative value, right? Now assume that this is integral. And so it's a root of, say, t to the n plus, it's integral of Vx, Vn minus 1x, t to the n minus 1 plus V1x, t plus V0x. Now I'm going to do this rather sloppily, like I already haven't been, but notice that what you're doing is when you take the nth power of this, this makes this a much more negative value, right? And here it's negative, but not as negative as this. And then you're multiplying it by elements of positive value, which makes the value bigger. So in other words, what happens is this negative value dominates, and these are all smaller values, right? There are smaller negatives, maybe even toward the positive. These all have positive values, and it's impossible to balance this equation. Because you have a negative value here that can't possibly be zero. The largest negative value here can't be canceled in a certain sense. And so that's why V of X, they are all integrally closed, so their intersection is. And so that's one way that you can apply this. Okay, any questions? Okay, just remember today I'm going to be out of the office from 11 to 12 because I've got our last calculus challenge meeting. Don't forget the math in on Saturday for last math club day, and our review session will be Wednesday at 5. I hope that's everybody. Thank you all for signing up. I hope you got something out of the class.